For this video lesson, we're going to discuss probably one of the more difficult questions in this course, how our weather moves across the Earth. So before you continue with this video, make sure you've downloaded that as well as the other two worksheets that are in this packet, and we're going to go ahead and complete them together. The activity following this video lesson will be to upload one of these worksheets to me. So please gather this, and when you're ready, let's continue the video. Take a look at this satellite loop of the Earth. It was created way back in 2004, and it's using an infrared satellite. So when you see the gray colors moving across the Earth, that's actually the sunlight hitting the ground, heating the land. But I want you to focus on the clouds and notice how the clouds that are around the equator or in the middle of the globe are typically moving from right to left, following that red arrow. And clouds where we are in North America and Eurasia and down in southern South America and Australia are also moving from left to right. That's two opposite directions. How in the world does that happen? Okay, we can see it also on this global loop. We're looking at the Earth's water vapor here, not clouds. But it's very clear that in the north and south, they're typically moving from left to right or west to east. Right in the middle of the Earth, it looks like they're staying still, but if you look closely enough, it's going right to left or east to west. If you look real closely, as some of the storms head towards the poles, they're actually bending backwards and going the opposite direction again from what we have here in the United States. They're going from right to left once again. So we're going to explain this motion in our atmosphere in this video lesson. Now, there's a powerful tool I'm going to access on the internet for this lesson, and you have to understand that today's date that I'm recording this is April 17th, 2017. This is the current status of our winds blowing across the Earth, all over the globe. And it's the same pattern. If you look at the United States, up towards the top, we have those lines flowing from left to right, or west to east. The same is happening down in southern South America, but if you look in the middle of the globe, again, they're going from east to west, the total opposite direction. So as we know and have established, it all starts with the sun. The sun is huge and it's shining on our tiny Earth, and the more direct rays are falling in between the tropics. The more focused rays produce more heat. The ones that are spread out at the poles produce less energy or less heat. So over time, since half the Earth is always facing the sun, the central part of the Earth gets warmer. So this is the current diagram of sea surface temperatures on the Earth. The ocean doesn't change heat as rapidly as the land does, so I picked the Pacific Ocean to look at this time. But I want you to notice that the warmer colors and warmer temperatures are right there along the equator in the center of the Earth, up to about Hawaii. And then as you get farther from the equator, the water gets colder. That's where worksheet number 1 comes into play, and I'm going to go back to my color and markers. This is the one that's labeled, where does weather go? And you have your lines labeled on there. The Arctic Circle, Tropic of Cancer, Equator, Tropic of Capricorn, and the Antarctic Circle. So we know that it's warmest at the equator, and we now know that warm air wants to rise. So let's go ahead and draw that here on our diagram. We'll put some arrows on the equator going straight up. What's hard here is I'm trying to represent a three-dimensional globe on a flat screen, and you're trying to do it on a flat paper. So these arrows that are going on the side upwards in the air, really in the middle would be coming out towards you. So if you understand that, we can continue. This air is going to rise up until it hits the stratosphere, and then it will have nowhere to go but spread out along the top of the troposphere. So some of it will turn and go north, some of it will turn and go south, well above the ground. This warm air wants to stay aloft. As that warm air gets closer and closer to both poles, it's going to get colder and colder. And we now know that cold air wants to sink. So when it gets to the coldest spot on our planet, we're going to have the air sinking straight down, like this. Now again, this motion that's happening above the Earth is happening in 3 dimensions. It would also be happening here in the equator, rising and going up towards the poles here and sinking down. As it sinks, eventually it's going to hit the ground and have nowhere else to go. So, once it hits the ground, it's going to start moving back towards the equator. And as it moves back towards the equator, it's going to get warmer. And warm air is going to get less dense. And eventually, when it hits its hottest point, it's going to want to rise. And now we have the cycle over and over again. We've got our air in motion, and this is just one big convection current. This motion here was conceived of by a scientist named Hadley. So this is called the Hadley cell. But I'm going to write in here, it's just convection. Something that we have talked about extensively in these video lessons. Now let's think about what's actually happening on the surface of the Earth. If I put you right here, standing on the side of the Earth, there you are, my little stick figure. Notice that the wind is blowing through your body towards the equator. It doesn't matter where I put you up here, the wind will be blowing towards the equator. The same thing will be happening in the south. It doesn't matter if I put you here or here or here. These wind currents on the surface are all blowing back towards the equator. So I'm going to use a different color and draw those arrows in. What you see on your screen now is a computer image of what we were drawing. We have the Hadley cell and we have surface flow moving towards the equator. But that's not what's actually really happening. That's not what we saw in the satellite pictures that we were looking at earlier in the lesson. That's because at the bottom of the stratosphere, the Earth has powerful, quick jet streams that circle the Earth like a donut. Usually there's 2 or 3 in each hemisphere. They're always going from left to right across the surface, or west to east. This is the current diagram of the winds at the height where we can find the jet stream. It's a little hard to see the United States buried under all those lines in that picture. But where the lines are close together and thickest, that's where the fastest winds are. You can see 2 main jet streams on this map. One is towards the bottom of your picture, heading into Mexico and towards Panama in Central America. And then it kind of leaves Venezuela going off the right of your screen. The second jet stream is coming in around California and Oregon, and it's crossing the country, and it's actually going over the United States at this time. In fact, that jet stream that's coming out of Minnesota and Michigan and going over Pennsylvania right now is helping to cool the upper atmosphere. As we make it colder aloft, that makes our atmosphere a little more unstable, and that's what's causing these clouds that are outside my window right now as I'm giving this lesson. So we have to account for these jet streams because they're very, very fast rivers of air. Imagine you were walking in a forest and you came across a little creek, and that creek was flowing at 300 miles an hour. Even if you creep up to it and just dip your toe into it, you're going to be whisked away. And that's what happens to the air in our atmosphere. So now we're going to use the second file that was in your download. It looks something like that. It's the Earth with the stripes on it, with the JS in the middle. Let's take a look at that paper, and I want you to see what exactly it's showing you. It says air motion is actually more complicated than what we had in the first drawing. So let's define what a jet stream is. A jet stream is a fast river of air. So what's happening here at number 1 is warm air rises at the equator, and that's happening because of density, something that we've extensively talked about. And then number 2, the air then heads towards the poles for the same reason as before. But then we get to number 3, we get to our jet stream. Now it's marked on this part of your diagram with a square, but remember it's a donut that comes above the planet here, and you're looking at the shadow of the jet stream there. All jet streams are moving this direction from left to right. So our air that's up here in the atmosphere, some of it gets swept into the jet stream and taken away. While for the rest of the air, it acts like a wall that it can't cross, and it sinks back down right here around the Tropic of Cancer. Then at number 4, it hits the ground, and when it hits the ground, some returns to the equator and some goes back to the tropics. So now let's think about what's happening if you are a person sitting right here on the edge of the Earth. Where you're standing at the surface, you now have the wind blowing away from the equator. So I'm going to draw those lines in this section right here. We're going to draw arrows all heading away from the equator like this. If you were standing down here next to the equator, right here, all the air is still moving towards the equator. The same thing's happening south of the equator. Right here at the surface, our air is moving towards the equator. And then down here in this area, if you're standing down, it'd be somewhere around Argentina, we would have the air moving away from the equator again. So this is our new map. Looks a little bit different, doesn't it? Here on the computer is another way of looking at it. There's our jet streams above the surface of the Earth, and there is our cell that is forming with the air rising at the equator and then sinking when it hits the jet stream. This is known as a Hadley cell. Now the Hadley cell is a lot smaller than it was before, isn't it? We also have air at the poles that creates its own circulation as it hits the pole and starts heading towards the equator before rising up under one of the jet streams. And the air in the middle is forced like a gear to move the other direction. That is called a ferrule cell. And that's what results in air motion towards the equator, close to the equator, and towards the equator at the poles. But in between, at the mid-latitudes, it goes away from the equator. So this is how the air should be moving across the world, but it's not. Again, as we take a look at this satellite picture, you can clearly see that in the mid-latitudes, it's moving obviously left to right, and in the equator, it's moving from right to left. So we're missing something, and that's the realization that our Earth is spinning. This spinning motion causes an illusion, which ultimately explains why weather moves the way it does. Let's think about a story that involves the polar bears up at the North Pole. I have an overhead here, which is kind of nice, that it will actually move on its axis. I can spin this like this. So here's what I want to do. I want to tell you the story about polar bears that have gotten really, really powerful over the years. Thanks to global warming and climate change, their habitat is dwindling, and they've decided it's time to unleash their secret nuclear weapon upon the United States. So the polar bears get together at the North Pole, and they plot in on their maps a line that goes straight up on this map towards New York City. Now this part of this overhead spins, so what I'm going to do is I'm going to trace this arrow as the Earth is moving, because that's what will happen once they launch their missile. So they get together in 3, 2, 1. The missile is launched, and I'm moving my pen straight up. But if you look at the ultimate path that the missile follows, it is curved. The missile did not curve. I drew a straight line. It's that the Earth moved underneath it. And instead of hitting New York City, it hits out towards Utah, safely in the desert. So let's do one more example. Let's say they go after England. Same thing. We'll do it again. We'll draw our map, which way the missile is supposed to go. 3, 2, 1. Missile takes off, but the Earth is spinning. My pen is going straight up, and it lands out in the middle of the ocean. Notice that the arrows here are curving to the right. Now, the natural enemy of the polar bear is the penguin. And thank goodness penguins and polar bears don't live in the same locations. So we're going to start here at the South Pole, and the penguins, they're going to fire a retaliatory strike towards the polar bears. But the missile's just not going to make it. They're going to go ahead and fire it this direction towards the equator. Okay, and they get together and count down 3, 2, 1. We're going to turn the Earth as I move my pen north, and it lands out there in the middle of the ocean. Note the spinning of the Earth here is causing the arrow to bend to the left. This apparent bending of the arrows is caused by the Coriolis force, and this video helps to explain that a little bit.
The Coriolis force is an apparent force that causes moving objects to appear to bend away from their intended paths. This force can be due to a rotating Earth, or in this example, a rotating platform. On a non-rotating platform, we can see that a thrown ball moves in a straight path to the receiver. Suppose the platform begins to rotate counterclockwise, just as the Earth rotates counterclockwise when viewed from above the North Pole. On the screen to the left, we see that the thrown ball moves in a straight line path. However, when we view the thrown ball on the rotating platform, the screen on the right, the camera reveals that because the platform is rotating, the ball in flight appears to curve to its right, and the receiver has to lean to the side in order to attempt to catch it. Even though the ball actually moves in a straight line, people sitting on the rotating platform see the ball appear to bend to the right of its intended path. The apparent bending of the thrown ball is due to the fact that the platform is rotating. The apparent force that causes the bending is the Coriolis force.
So this effect can be seen at a simple playground, much like Fred and Paul did on Weather World back in the 80s.
If the Earth were not spinning, the air would flow directly from the heated equatorial regions to the icy polar caps. However, these satellite pictures from Japanese television show that in the middle latitudes, weather systems generally move from west to east. This motion is a consequence of the Coriolis force.
We've come to the local playground to be able to show firsthand just how this Coriolis force works.
That's right. This merry-go-round is going to eventually play the part of our spinning Earth, and this baseball here will be a chunk of air. Now, here in this non-rotating world, if I roll it to Paul, it goes straight.
I roll it back to Fred, also goes straight. Isaac Newton long ago said in his first law of motion, an object going straight will continue going straight unless it's acted upon by a force.
That's right, but if we were to set this merry-go-round rotating, it would be a whole different world. Would you do the honors, Paul?
My pleasure, Fred.
Well, thanks, Paul, for the spin, and welcome aboard our private rotating world. We're going to try this rolling the ball trick again, and now we're pretty good at rolling curved balls.
That's right, Fred. You can see that each time it's deflected to the right, which is exactly what happens to all air motions here in the Northern Hemisphere.
That's right, you know, and it wouldn't look quite the same if we weren't on this merry-go-round. Let's take a look at how this looks from above.
From up above, the ball is and continues to go straight between us, meaning that the Coriolis force only needs to be considered for those who are rotating.
So now we're getting to the third handout that you were to download. It starts with, but the Earth is spinning. So we get the Coriolis effect, and that means arrows in the North Hemisphere bend to the right, And in the south, they bend left. So let's go down to the picture of the Earth that we have. Remember that here over the United States, we have wind arrows that are blowing away from the equator, like this. That's what we drew on our last picture. But now we're going to take this arrow and we're going to bend it to the right. So on this drawing, we're now going to have arrows that go this way. And next to the equator, where our arrows were going towards the equator, we're going to bend them to their right as well. We have the same at the North Pole. Now in the southern hemisphere, they bend left. So here we have an arrow moving towards the equator, and if I bend that left, this is how my arrows go. And also at the poles. And in the mid-latitude section where the arrows were going away from the equator, if we bend those arrows to their left, look what we end up getting. We end up getting overall motion right here in the middle. That's going this direction. Whether moving from right to left or east to west. And up in the United States, and down in the southern hemisphere in the mid-latitudes here, we have it going from west to east across the country. So you have an image on your notes very close to what you see on the screen there, and these different areas of global wind get different names. The global wind in the middle that goes from east to west are called the trade winds. The winds that blow over the United States from west to east, those are the westerlies. Typically, the trade winds stay within the tropics. That's how you can remember it. Trade winds and tropics, where the westerlies are here in our country. And at the poles, it's the easterlies. There is an area between the trade winds and the westerlies where very little air moves. Those are known as the horse latitudes. There's a famous legend that those are the areas where ships, as they cross the ocean, would get stuck and they would start to starve to death, so they would kick their horses overboard so they wouldn't eat so much food. Or sometimes they said people would eat their horses there. And that's simply just not true. People traveling across the ocean on ships in the 17th and 18th century knew how long it was supposed to take. And when your ship was horsed, it was riding only the currents. The wind wasn't blowing it. And when you ride the currents, your ship bobs up and down, much like you're riding a horse. So that's where it gets its names. In the middle, it's called the ITCZ, or the Intertropical Convergence Zone. Convergence is a place where the winds come towards each other. And if you look at that drawing, you see the arrows there are headed towards each other or converging. That means you have an area of clouds constantly over the equator, and we'll talk about that in a future lesson. So it's a very complicated process, but now you know why the weather in the tropics comes out of the Atlantic Ocean, and yet the weather here in Pennsylvania comes from Ohio and the West Coast. We'll look a little further at this in future lessons coming up.